That's the magnitude. Similarly, for the angle, you have to take the arctan of this divided by this, and since we know that the vector is in the right half plane, that you can use whatever your calculator gives you, it will be a negative angle. Okay. Yes?
Okay, so on like an exam, like if you, because the textbook has a different way of getting that final magnitude, finding coordinates. So would you ever be asked to give you?
How does the textbook do it? The textbook has to ultimately be doing the same thing. It has to be. Because there's no other way. You have to get the individual components, then add the components, then take the square root of the sum of the squares of the final vector. There's no other way that you can get it. If you can show me how the textbook does it, if it's different from what I just described, do so, but there's no other way that you can possibly get it. No. This is the vector. This is the magnitude of the vector. This is two components. This is an x and a y component. The magnitude is the length of the final vector. Yes?
In your exam for SHYs
I can't hear you.
in the exam, when you give the SHYs
You probably will have to use the numerical value for k because it doesn't want you to keep all these horrible denominators. It probably want you to do decimals, and in that sense, you need to put in the numerical value for k. Okay, any other questions about that? Okay, so again, I don't know of any other way you can actually solve this other than how I just described it. If you can find some other method, please show me, but this is how you have to do it. So does that answer your question about, yeah, so typically you want the magnitude. I'll pause for a moment in case you have any other, yes?
So could you have like knowing the length of each side of the triangle have found that angle?
What's that? Say that again?
Like knowing the size of each triangle, could you have found that angle and then using like sine, cosine?
Yeah, you could do that. You could do that. You could do that, however, I'm telling you that is equivalent to what I did.
Yeah.
And I didn't have to find the angle. This is an easier way. Okay, so okay, I won't give you that grainy. What's your name? Miss Marion. Okay, is that? Okay. That is correct. So what you may be referring to in the book is what the book does is it you find the angle and then you put in cosine of that angle. But what I'm saying is that usually you know the coordinates and you don't know the angle. And I'm saying why find the angle just to take the cosine of it and then it's equivalent to just using the coordinates. Does that make sense? Okay. Now another reason why I want to say that is because if you find the angle then take the cosine, it might not be clear that there is an exact rational number that is the correct answer. So if I found the angle and then did the cosine, I wouldn't see that there is this exact number that you can write out. This is exactly right. There's no approximation. Any approximation is something that is almost this. Does that make sense?
Yeah.
Okay, thank you. So that is absolutely right. There may be situations where you do have to find the angle, or where you're given the angle and you're not given the coordinates. But almost always you're given the coordinates. Yes?
I just wanted to ask if we will be allowed to use calculators on the exam.
Yes. You'll be allowed to use calculators. You're allowed to use graphing calculators, however, I do not recommend it. I recommend that you use regular scientific calculators because graphing calculators are a little bit, it's easy to put them into modes and not know what mode they're in. Again, as I said last time, there was a student who only right before the final exam realized that all year her calculator was in radian mode instead of degree mode. And then asked, can you give me points back for all those questions? I said, I'm sorry, I can't do that. So instead what I did was I brought calculators, and I brought her a calculator, and I showed her a degree and radian. So you see on the scientific ones, it always says degree or radian right there on the screen whenever you do a calculation. The advanced ones maybe don't do that. Okay, so again, thank you, Miriam, for pointing that out, that the book does all these angle things. And, you know, maybe you like that, right? Maybe you like the angles, maybe you don't like this weird thing I did. Maybe you'd rather just put in the cosine. But, you know, honestly, I think I like this better, and it's the same. And it's actually, it would have been more steps, in my opinion, to calculate theta. But again, you don't actually need theta, right? You just need cosine of theta and sine of theta. But if that's what you need, that's just a ratio of the numbers that you actually have directly. Does that make sense? You're nodding, does that make sense? Okay. So this is what, yes?
And then that was because this example was a 3, 4, 5 triangle.
Right.
But if we didn't know that and we had to find the y, then maybe it would be more difficult.
I have the opposite opinion. If this were not a 3, 4, 5 triangle, if it was just some generic triangle, like this is 11 and this is 17, do you want to find the angle? Wouldn't you just like 11 over the square root of the sum of the squares? Now the square root of the sum of the squares is still a horrible number, but you can just do that in one step. You don't have to stop to find an angle. And then take the cosine of that angle. Does that make sense? Okay. Now also a 3, 4, 5 triangle is not a 30, 60, 90 triangle. It's close, but it's not. So be very careful. I remember one of my first experiences with not trusting AI was late one night. I was doing grading, and I went, wait a minute. Is it 3, 4, 5, a 30, 60, 90? I went, it's not. And I was looking, it's like the numbers are close, but it's not. And then I typed in, I was going crazy. I said, is it within the 30s? And then on Quora, which I know all of you probably use to do homework, at the top was an AI-generated answer. And it said, yes. Yes, it is. And I went, okay, no, that's not true. So be very careful. AI hallucinates, which is a fancy way of saying it statistically generates the most likely answer to a question. And if the most likely answer is wrong, then it will give you the wrong answer. Okay? So common errors will be commonly wrong answers given by AI. This is why AI can't do logic problems, because we can't do logic problems. And we all make mistakes with logical problems. So, anyway. All right, so the lesson here is that this is horrible. Okay, this was a horrible thing, and I even made it as simple as possible. This is absolutely atrocious. And if you wanted to simulate this in a computer, it's horrible, because actually computing, even whether you wanted to calculate angles or take the square root of a sum of the squares, that's bad. That's computationally expensive in a computer. It's time consuming for you. And so the rest of the first half of this course will be to get away with never doing this again. Can we find a better method? Right? Doc, are you texting?
No, I'm sending it to
Oh, okay. Maybe do it afterwards. Maybe send it afterwards. So that's what I want, because everyone is giving good input to this, and I'm missing this. I want you to be on point. Okay, thank you very much. All right, so remember the first semester where you first did all these force problems, where you're adding up all these force vectors and you're tugging on a string and there's a box and it's gravity, and it was horrible. And even though it was horrible, it still wasn't good enough for problems where the force wasn't constant, right? Because all of your kinematics formulas for saying what the motion of a particle is going to be required that the acceleration was constant, which required that the net force was constant. But that was then not true immediately when you have a general gravitational force, or you just have a spring. So what did you do next? But you were able to figure out how high a ball goes when it's ejected by a spring. You didn't use forces though. What did you use? Raise your hand. Hold on. Yes, sir, in the back. What's that? The area? you know, technically what you're saying is correct, but I want like a physical quantity or a methodology. You weren't always finding the area under the curve to answer those questions. Yes, the energy. What's your name, Miss? Glenn? All right, Glenn. So I'll answer. What's your name, sir? Say that again. Call you Dieter? What? D-I-D-I. Okay. Stay out of my laboratory. Anyway, and then Glenn. Sure you get that a lot. Okay. All right, so we used energy, right? We used energy. We didn't use forces. Okay? Now, there was a problem with using energies, namely that in order to use them, the energies don't tell you which way the particle is going to go. You had to know which way the particle would go. The energy would just tell you when you got some distance along that path, how fast it would be going. So the energy wasn't entirely useful. It turns out that there is a much more advanced energy theoretic version that actually also tells you the direction in which you go. It's called Hamiltonian mechanics, where you literally use the energy to crank out what is the direction in which you're going to go. But that's kind of, it's a lot, but that's actually how you normally solve these kinds of problems. Nevertheless, we need to keep track of some information about directions. So we're going to go to energies almost exclusively. However, direction of travel might still be important for electrons and protons. Now, something interesting about electrons and protons is that they're very tiny and they're very light. So even though objects tend to have inertia, if you have a big heavy shopping cart and you're pushing it, it's not always going to go in the direction in which you're pushing. Right? If you push it for a while in this direction and it just keeps going, and then you try to push it to the side, it's not going to immediately start going that way. It's going to kind of slowly bend around. That's its inertia. Inertia is a property of mass, that is its resistance to having its velocity change. So it's F equals m times a. However, if that m is very tiny, then the inertia is very small, and effectively, it will just travel in whatever direction you're pushing it as fast as it can. So if there's nothing in the cart, and you push it for a while this way, and then you push it this way, it's just going to immediately start going in the direction in which you push it. Electrons and protons are so tiny and have such small mass that they will basically just go in whatever direction you're pushing them. It will be accelerating, sure, but they're going so fast and they accelerate so fast, you might just see them zip around along certain lines. So for that reason, the actual direction of the force will matter, because they will tend to trace out streamlines along the direction of the force. Now, again, because they're so tiny and they have so small mass, it kind of doesn't even matter what the magnitude of the force is in that context. If you care about the paths they're taking, you just kind of care about the directions. And furthermore, you don't really care about the fact that when you put a single particle down somewhere over here, that's actually going to change the forces on all the particles, right? They're all going to start interacting with each other different. You add one more particle, and now that's going to be pushing and pulling on everything at the same time. Kind of what you normally have is you have a bunch of particles that are just somewhere, and they're creating, how do I put this? They're just fixed, they're not moving, and then there's one little charge you put in the system. And then it's gonna move around. It's gonna be pushed by all the other charges. And so the relevant idea there is, okay, what force is it going to experience at each point in space? And then what you end up with is the notion of a force field, right? Because if I took this charge and I put it here, it would experience a net force in a different direction. If If I put the point here, it would experience net force in a different direction. And so given some configuration of fixed particles, with signs and whatever, associated with that configuration of particles, there is an assignment of a force vector to every point in space, which I might like to say is the force that would be experienced by a charge of 1 coulomb, for example, if I were to put it there. Okay, you starting to see what this is a kind of an odd idea, but I'm trying to bridge the gap to what we're about to do. Okay, so let's sum. What am I talking about? I'm saying, let's say I have a bunch of fixed charges all over the place. Some are positive, some are negative, and they're fixed. They're held in place. They're in like charged up capacitor plates or what have you. And then I take a little tiny particle and I put it right here. And if I put a little tiny particle there of, let's just say, 1 coulomb, it will experience some net force. You know, you do all this kind of stuff. You might experience a net force like this. But if instead I put the particle over here, it might experience a net force, I don't know, maybe like that. And if I put it over here, maybe it's a net force like this. Yes?
What the direction of the net force was to go from?
It is. It is due to the other charges in exactly the way we just computed. Okay, I'm just saying, let's say we went through this whole process every time I put the charge in a new position. Okay? So every time I had a different position, I had to go through this entire process again, which is lengthy and boring and complicated. And the end result is a vector. Okay? So what ends up happening is, okay, and once I know the vector, now if this had a large mass, computing its actual trajectory would be very complicated. But since it has a very small mass, it will approximately just flow in whatever direction it's being pushed. Approximately. Okay? So the direction of these vectors that you would calculate if you put it in a fixed position, these are relevant. These are relevant ideas. But you don't actually care about where you put the charge. You just want to know what would the force on the charge be if you put it at any given point, but you could put it anywhere. So instead, what you like to think about is, let's say I have a bunch of charges, and let's get really abstract. Okay? Now let's just say, if I were to put a 1 coulomb charge at any particular place, that charge would experience a net force pointing in some direction. I don't know. In some direction. And there's really one of these at every single point. And then you can connect a bunch of these together. This is called a force field. This is a field of forces. A force field is, so force field is a function on space such that there is a direction associated with every single point in space. So one way to think about it is, imagine you're in a river and the water is flowing, and at every point in space the water has a certain velocity vector. That's telling you how you're going to flow with the water. Right? It's not quite the same thing, because this is force and that would be the velocity, but you also know that there'd be a force on you. And since the water has so much more momentum than you do, you're basically just going to flow whichever way you're being pushed. But wait a minute, there's one more thing that we don't actually care about. We don't actually even care about how big the charge is that we place there. Because I just said that the mass is so small that it's basically just going to move along what are called streamlines. It's not really a streamline, but let's just say streamline. It's basically just going to flow along the streamline no matter what the charge is, as long as it's small enough, as long as it's not macroscopic, it's a little tiny dot. So we don't actually even care about the size of the charge. Now let me specify, if the charge is actually negative, then it will flow in the opposite direction. So this is where things get kind of weird. If the charge for something like -1 coulomb, and I put it here, it would flow in the opposite direction along the streamline. Okay, yes?
So that's the negative in this case, but for a strictly force, but there's another way we can calculate the force, because we learn. And if the charge matters in that case, which can impact the president for the first time in theory, then
Yes. Okay, so there are two things we have to distinguish. We calculated the force. We did not determine the acceleration. We did not determine the actual trajectory of the particle. Okay, my point is that when when m is very small, then for any given f, a is going to be enormous. Okay, the bigger that m is, the more that the particle's motion resists changes in its velocity. That's inertia. If the mass is almost nothing, I put it to you that it will basically move in any direction in which it's being pushed, almost instantly. So although the particle will not exactly flow along the streamline, it will deviate a little bit from it because it does have some inertia. It will very closely follow the streamline as much as you care to. Okay? For any amount of charge, even if the charge is really tiny, like the charge of an electron, the mass is yet so much smaller by orders of magnitude that this argument still tends to go through. Does that make sense? Okay, so they're different things. So even though, yes, the charge matters, the mass of an electron tends to be so much smaller. And also, if this is a macroscopic configuration of charges, they're going to be exerting an enormous amount of force on it. So it's very difficult. We don't have an intuition for this because the electrostatic force, from the perspective of, say, electrons, is so much more powerful than the gravitational force that we just can't even picture it, right? If the example given is, you know, if my fist were fully charged with negative, just fully, every atom had an excess charge of -1, and your fist had an excess charge of -1. The repulsion that my fist exerts on your fist would be like thousands of times greater than the gravitational force of the Earth. It's just enormous. I don't remember exactly what the number was, but it's huge. Okay, so a lot of things are very different in this context. You're gonna have to start thinking a little differently. Yes.
I wanted to ask if amount of the charge matters. Like 1 coulomb is very small, right? So
Yeah.
if it was
And even an electron has a very tiny amount of charge. What I'm saying is that even that amount of charge is great enough for it to effectively flow approximately along streamlines.
okay. So if it will be more coulombs,
Yeah.
how affect the path?
It will just be even more approximately along the streamlines. It will have even less deviation. Now this is all very approximate. This is not exact, okay? It's all very approximate. Okay, so even an electron by itself is already approximately going to do this. If you add more coulombs, it's going to even be close. It's irrelevant. The point of this is that even in spite of all of this, all of this story, that's not really the most helpful thing for just quickly knowing, okay, which way are the charges going to flow, right? They're all basically, no matter how much charge and how heavy they are, they're basically all going to flow wherever they're being pushed. Does that make sense?
Yeah.
It's like if you have a river and you're throwing stuff in the river, does it matter if it's an apple or a leaf? No, the river is so powerful. Everything is just going to flow along with the river. And even if you're in a boat, you're gonna go downstream. You basically can't even fight against it. Does that make sense? So at that point, it becomes more important to talk about the shape of how the river is pushing things than the mass, the charge, anything like that. Does that make sense? Okay, so we're going to change our perspective to adapt to looking at how the river is pushing things. So the last step, now understanding that if it's a negative charge, it flows in the opposite direction. Okay, that's important. But it's confusing that the actual charge carriers that are mobile are electrons which are negatively charged, so they're actually always going to be flowing in the opposite direction. Blame Benjamin Franklin for that. We're still going to take as our reference positive charge. And positive charge will always flow in the direction of the force, not in the negative. but electrons will flow in the river. So, okay, now I'm ready. Okay, I don't actually even care about this. Okay, so what we want to do is we want to talk about the net force on something, but where I don't care about the charge. Okay, so look at the magnitude of the Coulomb force. Okay, let me actually change it. Let's say I have a little q that's the test charge, this little tiny guy, and the capital Q is the charge of one of these other charges, and I have to add all of them up, right? There can be a whole bunch of them. They're all going to have different distances, different charges. But when I add them all up, each of those terms has this little q in it. I don't really care about the little q. It's common to all of them. So if I have some kind of net force on that little guy, that factor is going to appear everywhere. So I'm going to have a sum over all of these forces. But that's in there, and again, I don't care. I don't care how big the thing is that I throw in the river. So what's a natural thing to do is to say, okay, instead, define a new quantity. Define a new quantity here that is Q, and this is a magnitude, and that's absolute value. This is not a magnitude, so the sign matters. That's Q, which could be positive or negative, times something else. And that something else is the electric field. Okay, from now on, E will stand for electric field, not energy. And this is the net electric field. Okay, so this is our way of talking about which way the river is flowing, not the actual force and inertia of any object flowing down the river. We know that we can yank this guy out of this entire expression. It does work that way. I didn't explain that it actually does work, but it works. And so we have something called the electric field. And now this is really useful. Now this is really useful because now what we say is there is a new force, there's a new field. It's not a force field, it's something else called an electric field, which is in fact a field that assigns arrows at every point in space. Right? And if I were to put a point charge of some charge Q at a given point, and the electric field at that point is that, the net electric field, then the net force on the charge would be simply Q times that electric field. Okay, why are we doing this? This seems silly, but again, we're trying to forget about this horrible process, and we want to move to a new paradigm where we're just talking about how the river is flowing. Does that make sense? Okay, this electric field is simply a statement about how the river is flowing. If I were to put the electric field is due to all of these other charges, and if I wanted to know what the net force on the given charge that I put down would be, I take that amount of charge times the electric field, and then I get a force. Now I do that instead of recalculating the forces every time. I have a field of, that's why it's called the electric field. So let me draw it. So now we have a new paradigm. New paradigm is in terms of the electric field. And it looks entirely similar to the force. You go, why would you do this? Who cares? I'm telling you it's useful. When we get to magnetism, there will be no alternative. You absolutely have to introduce something called a magnetic field. There's no way you can talk about the force directly. So this is setting us up for that, yes?
So here's my question. So the electric field is just Q, little Q times big Q over R squared, right?
That's the electric field contribution. Hold on, let's go one step at a time. So there is an electric force that is exerted on each point particle due to each other point particle. So let's say due to a point particle, only have 5 minutes left. So the force on a single point particle is going to be, okay, let me just write the full general version, if not without signs. Please forgive me for doing this. R to the 3/2, is it? Yeah, R vector. Okay, just trust me. That's the full version without manually inputting plus and minus signs. If you don't like this, I can write it like R cubed, and this is R hat. That's the unit, the vector of unit length, pointing from one vector to one point to the other. This is a thing whose components are just sine and cosine. Okay.
That's what you get 3/2 from.
3/2 was if this isn't the unit vector. If it's the, it doesn't. Remember when we did the problem and we found that there was a factor of R cubed in the denominator? I'm telling you that there's a, look, I'm just doing this so that I can answer your question, so I can literally pull out the Q and I don't have to take absolute values. Okay, this is the, we can talk about this later, just trust me, you don't have to use this formula. I'm trying to give you a better explanation than in the book. This is the force due to a point particle. I can write this as Q times some other quantity. Okay, this is a vector. And I can write this as Q times something that I might call E. And so this is the electric field at a point due to a point particle. Okay, so on the one hand, let's say I have a big Q here, and I have a little q here. The big Q exerts a force on the little q given by this. Okay, just forget about this. This is a vector and it's being rescaled and it has a sign and whatever. Okay. This is the force. I can also think about it that let's say there were no charge there. I just had this fixed charge. And this fixed charge puts down an electric field at every single point in space. And the magnitude of that electric field, due to that single point charge, is going to be KQ over R squared. Okay. Oh wait, yeah, you're right. Oops. Sorry. I overcorrected. This. Sorry. Because this is a vector of length 1, so it has unit length, so this is the magnitude. Sorry. This is the magnitude with sign, and this is just the direction. I'm sorry. This is direction is just a vector whose components are sine and cosine, so that it has unit length. Sorry. So the magnitude of the electric field is that. Now, if I were to put a point charge of charge Q here, the force on it would be a rescaled version of the electric field at that point. Specifically, I rescale it by the charge I put there. It's a completely almost trivial thing to do. Why do I even want to do that? I'm only doing that because I want to imagine that the forces, I don't care about the force that the river is exerting, force that the river is exerting on each apple and each leaf. I just care about looking at how the river is flowing. The electric field is how the river is flowing, yes?
Isn't there supposed to be no square on the R in the electric field?
You're thinking of the electric potential. Okay, so but for the electric field it should be like that. Okay. We'll continue next time. Sorry about the little typo. Anyway, this is very conceptually confusing, so I'm taking extra time. I made the chapter 16 and 17 homework available.